The fourth point is distributed consistency. I believe this is the most challenging part of the system. In a distributed environment, the hardest thing to handle is the gap between intention and reality. Because of the matching characteristics of exchange transactions, once an order is submitted, the time it is executed is uncertain. If a user submits multiple orders, due to the uncertainty in execution times, the order of execution is also highly uncertain. However, we must pre-freeze resources before execution, and if pre-freezing occurs, we consider it an open position transaction. But after execution, the user's position status might treat this order as a closed position or even a position reversal. Therefore, handling it requires extra caution. Here, I'll use a timing diagram to illustrate a scenario, allowing everyone to better understand the detailed analysis of this issue. Our system operates on a unidirectional position basis, meaning that a user's position is. At any given time, it can only be long, holding a long position, or short. If their position is short, what about when it is long? If they place a sell order, they are closing the position. If they place a buy order, they are opening a position. But if they are in a short position, placing a sell order would be opening a position. Placing a buy order would close the position. So, user orders are either buy or sell. And because their position can be long or short, this forms a two-dimensional matrix with four possible execution scenarios: buy, long, buy, short, sell, long, and sell, short. Okay. If anyone is not familiar with exchange contract trading, they can learn more about it. Now, to introduce the acceptance level of this concurrent distributed trading scenario, I need to first explain the entire scenario from order placement to matching to settlement in a decentralized context. After explaining this, I will introduce the first layer of handling special cases after the settlement in this scenario. When certain conditions are met after settlement, two more transactions might be initiated for compensation or correction operations. And when initiating these transactions at these points in time, if resources are moved or occupied by other threads, or if there are insufficient funds, how should it be handled? Okay, let me first introduce the entire trading process. As mentioned earlier, when users place orders, they can place buy or sell orders. After placing an order, it will go to the position, first checking the user's position. What is their current position status, long or short? By using the four possibilities of this two-dimensional matrix, we can determine if the user is opening or closing a position. If it's opening a position, we need to pre-freeze the user's margin and pre-deduct fees. After execution, it will first go to the account service, and these pre-deducted fees and margin will be subtracted. Then the user's position will be increased. A note here is that the pre-deducted margin could be the taker fee or maker fee. Then, depending on whether it is a taker or maker during matching, we decide which fee to collect. Therefore, when freezing, we need to pre-charge based on the highest taker fee rate. Then, during settlement, based on the pre-freeze records and whether they were a taker or maker during matching, the fee difference is refunded. Okay. If a user is determined to be closing a position, they don't need to freeze the margin. They just need to preemptively freeze the position they want to close. After the matching is completed, the position is deducted and the margin is released from the position. Then, through the event to the accounting account service, add this margin back to the account into one's own account and perform some platform account operations for accounting purposes. This is the basic trading process, and you can see it slightly doubles the complexity of a regular distributed trade. Okay, now let's first talk about a scenario. Now let's introduce this second scenario. It was mentioned that when a user places an order, it is determined based on the position status, whether it's opening or closing. But now there's a situation. Assume it was initially judged as opening a position, and then it comes to this matching and settlement path. Then, when the settlement reaches the position to increase it, it is found that the position status has changed from opening to closing. How should this be handled? At this point, 2 more transactions need to be initiated. The first transaction is to reach the previous step's account service. Conducted as it was previously considered an opening, the margin and fee were deducted, and this needs to be refunded to the customer. Now this transaction becomes a closing, so a transaction request must be initiated to settle this closing transaction. Then this request is addressed to itself, so it actually just executes an internal function. Then it will execute the closing operation, and after closing, release this part of the margin, trigger an event, and then have it released by the account service. This is from opening to closing, specifically the settlement turning into a closing position. The second part is from closing to opening. Initially, when closing, the position was pre-frozen. But after settlement, the process reaches the POS machine and finds that the original closing order has turned into an opening one. What should be done at this point? At this point, a batch of requests needs to be made. At this point, instead of proceeding to the settlement step for account, we handle it directly. This request is to execute the action of opening a position. And it also involves deducting the margin and fees. After deduction, increase the position. However, there is a problem here. That is, at this point, the deduction of margin and fees may lead to insufficient funds because they weren't pre-frozen. So how should this be handled? There are 2 approaches. The first is the official exchange approach. If there isn't enough money to deduct, it will trigger a forced liquidation mechanism to forcibly close the increased position. This is the official approach of the exchange. But since this project hasn't reached the stage of implementing a forced liquidation mechanism, in this initial phase, I'm using a second, simpler approach. That is to allow the account to go negative, and then during the initial risk control check. When the user's balance is negative, they will be reminded to replenish their balance before they can place orders. Also, they cannot perform opening operations. They can only perform closing ones. Now, as we can see here, the handling method for the 2 special yellow scenarios where the balance is insufficient has already been explained. Now, I'll introduce another situation here. The scenario here is that when a user initially opens a position, after settlement, it turns out to be closing. Then they initiate this transaction. on-site request. Here's the issue. Suppose the user currently holds 5 positions, and at this time they place another order to close 3 positions, so 3 positions are already frozen. 5 positions, 3 are frozen. Then this order to convert from opening to closing a position happens to involve 5 positions. Okay. 5 positions, 3 are frozen. Now, to close 5 positions, what should they do? Currently, there are 2 approaches. The first approach is not to design the system as one-way position holding, but to switch to two-way position holding. However, this change is too significant. All logic regarding one-way position holding needs to be modified. So this is not our ideal solution. The second, better solution is stealing, seizing resources from other threads. So when a request comes in to close 5 positions, it finds that out of the 5, 3 have already been frozen. Then they seize the 3 frozen positions, close them, and release the funds. Then, when the original request to close 3 positions settles, it will return to our process. The process of closing and then opening positions follows this blue path. This forms a closed loop. Finally, let me add something. In this trading process, at the beginning, when determining positions, it's used to decide between opening and closing positions. The step of freezing positions should be merged into this step for atomic execution. If the position feedback determines it's a close, then the order service should execute the order, and these 2 steps should be atomic. Secondly, all trading stages before matching need to have a rollback compensation operation process. The third part is that each transaction in MEC involves both buyer and seller. So when doing synchronization, it should be done from both dimensions of buyer and seller. Also, if your trading process triggers these compensation operations, you need to pay extra attention to the management of idempotency keys. The final part is that this trading scenario currently applies to limit order trading scenarios. If you're using, I misspoke, this is for market order trading scenarios. If your trading scenario involves limit orders or other strategies, further expansion is needed based on this. This is something our exchange hasn't done yet. We're only completing the core foundational part first. After breaking down the basic trading process and points of attention, we can now return to the original topic, the Phillips protocol and the Phillips scenario. Now let's look at the user's sequence diagram to understand the usage scenario. Suppose the user's initial position state is 10 long positions. 10 long positions, right? Then at this moment, they place an order to go long for 130 positions. Then the order of 130 long positions is sent to the matching engine and is queued, awaiting execution. Then an interference event occurs. A long submitted order B to sell 30 positions executes, causing the position to reverse to 20 short positions. Now his order A of 130 positions finally gets matched successfully. At this time, with 20 short positions, how should this be handled? That brings us back to what we mentioned earlier. There are three possibilities. The first possibility is, it's simple. Opening a position becomes closing a position, reducing the current position. The second possibility is that opening a position becomes closing a position, but it happens to close all positions, terminating the position. What's the third possibility? That's it. After opening a position and turning it into a closing position, if the quantity is not enough to close, it turns back to an open position. For example, there are currently 2020 short contracts, and he currently has 30 long contracts. So after closing 20, he needs to reverse and open 10 contracts. This is what's called the Phillips scenario. He needs to open a position, turn it into a closing position, and then open again for the part that wasn't closed. Handling this part simply requires using the scenario process we mentioned here to combine it. Then you can handle this scenario correctly. Okay, let me add something that was mentioned earlier. When handling 20 short contracts, there are three situations: either close the position, close completely, or open in the opposite direction. Now, with the addition of a fourth scenario, say these 20 contracts have another 10 pre-frozen by other orders. In that case, how do you handle the 30 contracts mentioned just now? At this point, we return to the step mentioned earlier, seizing resources from other threads and taking over those resources. Take them over and then process all 20 of these orders. After processing all of them, close them all out. Once all are closed, open 10 in the opposite direction. Open another 10 in the opposite direction. Then, if the originally frozen closing order is executed, as mentioned earlier, follow the process here, the blue process, and continue. In this way, the four Phillips scenarios can be handled completely. This is the complexity concerning the Philip protocol. You must first analyze and break down all the situations into the basic cases here. After handling them, you can then deal with the occurrence of the Phillips scenario all at once.